Hi everybody, welcome to the first section in discrete math, section 1.1, propositional logic. A proposition is a declarative sentence, because you can read the definition, but most important, it is either true or false. We say either, we mean true or false, cannot be both. Right, so here's some example of proposition. The moon is made of green cheese, so that was false. Trenton is the capital of New Jersey. It is true. Toronto is the capital of Canada. That is false. Ottawa is the capital of Canada, so it's not Toronto, so that is false. 1 plus 0 is equal to 1, so that is true. And 0 plus 0 is 2, that is false. So we can see that it's either true or false. And as in the English language, when we say about declarative sentence, we end up with the period. So when we have something like exclamation point or question mark, this is not a proposition. X plus 1 equal to 2. Well, this is if x equal to 1, then it is true. If x equal to something else, it's not true. So it could be true or false, depends on what values of x. And likewise, depends on certain values of x, y, or z. This statement, or we say that this proposition may be true or false. So those are not proposition. Right. The notation, we just use the lowercase letter starting from the P, so P, Q, R, S, and so on, to denote proposition. The proposition that is always true is denoted by T, so that's what we have been doing, true with the T, and the proposition that is always false denoted by F. On the calculator, true is 1 and false is 0. So that real quick, for example, 1, let's say hit second and then test, is 1 equal to 1 plus 0. We know that it is true, right? So the answer is going to be 1. Now, I just highlight that, hit enter, and this is not true. The answer should be 0, right? So in computer science or in calculator, true is 1 and false is 0. Right. Of course, we use the calculator a few more times. Compound proposition and logical operators. Compound proposition is a proposition constructed by combining using the logical operators. Logical operator is the operator that combines the proposition or do something to it. So let P be a proposition. Now we define the first one is negation. Just by the name HHS, it means not. So we send negation of P, we mean not P, and the notation that we use in the book is that simple than P, so that is not P. All the books use the bar on the top to denote the negation of P, or use a tilde in front of P to denote the negation of P. What it actually is, if P is the proposition, then not P is, we just throw the word not into it. And here we'll give all the true values for the negation of P. So the true values of P is the opposite of the true values of P. Let me say that again. The true values of negation of P is the opposite of the true values of P. It is misleading if I write like that. So to say the true values of negation of P, which is denoted by this symbol, is the opposite of the true values of P. So if it is true, negation of P or not P it will be false, and if it's false, it's true. So that's pretty straightforward, right? So let's turn the true into false and the false into true, therefore negation. Right. Now, let's see how it works. Write the negation of the following statement. Michael's PC runs Linux. So if we want to turn that into a negation, all we do is just throw the word not, make the sentence to the opposite values. So we say the negation is Michael PC runs. So we say does not run Linux. Right, so that make it a negation. And now the earth is flat. Like that, true or false, doesn't matter. We just change the negation to that. So we're just going to say it's not flat. We just throw that in and make it a negation of the statement. Right, so that's all we have. Now we have a little interesting problem here. It says that once upon a time there were two identical twins. So let's say, and who live at a foot of the road. So this is like their little house here. And so it is a foot. One lead to the city and one lead to the forest. And the problem here is every time anybody come to the fort, they only see one twin. Alright. So one of the twins always tell the truth and the other always tell lies. And also another problem is that the travelers saw only one of the twins and could only ask one question. So that, of course, in real life we don't have all kind of these scenarios, but it's fun to think about the answer for those type of problem. So once again, identical twin, you only see one of them. You can only ask one question, and can you ask that one question so that it will tell, so you know which way will lead to the city, which way to lead to the forest. The key here is one question, and you can only see one twin, and that one twin can either say true or false. Of course, they are identical twins, so you don't know which one which. And you can only ask one question, so you cannot verify. If you can ask more than one question, you can verify if that is the person telling true or lies. So we don't know that. So one question. So what do we think? Of course, if you're just asking which way to the forest, they might point in the true or false. You don't true or lies. You don't really know. So I thought you have some time to think about that. Now the answer is this. Of course, you cannot just ask a simple question like which way will lead to the forest, which way to lead to the city. That's not going to work. Have to be a little more creative here. So the answer to that is, and just add one word to it. So usually you say which way to the forest or which way to the city, right? I just add usually which way you would say led to the forest. Let's see. Let's say we want to go to the city. So we ask this question. And then the key here is this. So why one word make the whole thing different? Now, let's say if we don't have that. Of course, the true person will tell the truth. So he usually send the true. So he will tell the true again, and he point in the same direction. He always pointing, which is to the city, which is good. The true will always tell the true, and he will tell that he will point in the same direction that he usually point to the same direction, which is to the city. So that's good. That the person tell true. The person tell lies. Usually he will point in the wrong direction. But because we have to add the word usually in it, he have to point opposite to what he's always doing. Right? So usually he point in the wrong direction. But because he tell lies, he have to opposite. He have to point in the opposite direction of the wrong direction. So opposite of the wrong direction is the right direction in this case, because there are only two options here. Right? So throw that word will make everything works out perfectly. Right, so that is negation. True turning true into false, the false into true, and negation of negation. We get back to the statement or the proposition. Right, now we have the conjunction. Conjunction, let P and Q be proposition. The conjunction of P and Q denote as that with that, and we just read N is the proposition P and Q, and the conjunction. By the way, if I have to say something to denote that symbol, let's call that a wedge. So the conjunction P wedge Q, that doesn't flow. Let's just say P and Q. So P and Q is true when both of P and Q are true, and false otherwise. So now we have two proposition P and Q. One of them can be true or false. The other one can be true or false. So let me just write this down. P can be true or false, and then Q can be true or false. Now, true to true, right? So the first one, if it's true, it can be go to true or to false. Second one, false. First one, false, it's going to go to either true or false. Right, so as you see, there's 4 different scenarios. That's why we have 4 rows here. Better yet, just write it's a tree like this. The first proposition could be either true or false. Doesn't matter what it is. The second proposition can be either true or false. So we have true, 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 false, false, true, and false, false. Right. So let's write that out. And you see that will be true, true, and then false, false for the first one. And then the second one is true, false, true, false. Later on, there's a way systematically doing this. The one on the rightmost is alternating every true, false, so true, false, true, false, true, false, and so on. The one on its right will be alternating for every 2 of them. True, true, false, false, true, true, false, false, and so on. Right. Now the rules here say conjunction of P and Q is true when both of them are true. So true when both are true. So this will be true when both of them are true. So we focus on this. And it says it will be false otherwise. Right. So it have to be true. Both of them have to be true in order to be true. For example, I just give you this. Let's say the rules for the selective service: every male between the age of 18 and 25 have to register for the selective service. Of course, if you register, then you have to, for example, if you apply for financial aid and you are male under between 18 and 25, you have to sign up for the selective service, those kind of the things. Right, so the thing is, with that, you have to check both of the boxes so you can sign up for the selective service. You have to have both of this, right? So in order to be true, both of them have to be true. So that's what example that I think is very good one to think about this scenarios. So it's true when both of them are true, and false when everywhere else. So just gonna denote that true and true is true. Of course, later on we're not going to use the equal sign, but we use that equivalent. But let's just use correctly with the 3 line. Right. Let's look at some example here. Let P denote the statement it is raining, Q denote the statement the sun is shining, and R denote the statement the sky is dark. What is the following in sentence in logical simple? The sun is shining. Oh, so that is Q. But it is raining. P. Right. Even though we say it is and, but in fact it could be anything. That means both of them. So the but here actually it's just going to be a wedge or a conjunction. So we might say this P and Q, but also maybe P but Q. That's also fine. Alright. So the but here also denoted by the wedge or the conjunction. P and R. P is it is raining. It is raining, and the sky is dark. Right, so it is raining, which is P, and the sky is dark, it's R. Right, so that is conjunction. Conjunction is true when both are true. Now we have disjunction. Let P and Q be proposition. The disjunction denote as P and Q. P or Q. We use like this symbol called a V, because that looks like a V. It is or. The disjunction P or Q is false when both of them are false, and it's true otherwise. So this is the rule. False when both are false, and it's true otherwise. Right. So the scenarios are just like last time. True, false on the rightmost, and then on its left, alternate every two, true, false. And the rule says it's false when both of them are false. So we focus on that. Everywhere else is going to be true. Right. So turn to another example. So let's say 2 years ago, at the height of COVID, and you want to go on a cruise, and the requirement to get on the cruise are two things. Either we have to have a proof of vaccine, I'm talking about some kind of, I mean, of course, the policy may not be different, but I'm talking about either proof of vaccine or the COVID positive within the past, I mean, have to be 15 days or more, something like that, COVID positive. Right. So if you want to get on the cruise, either to check one of the two boxes, right? So if you check one box, it's good enough to get on the cruise. If you check two boxes, even better, you still get on the cruise. The only case that you cannot get on the cruise is you don't check any of these boxes. So it is false if both of them are false, and it's true when only one of them is good enough to be true, and if both of them are true, it's still fine. So both of them true is still true. Right, here's some example. If P denote I am at home, and Q denote it is raining, and P or Q denote I'm at home or it is raining. So it's or. So we use that simple. Student takes physics or student take chemistry. That's perfectly fine. Right? But when you say like this, a student can take both of physics or chemistry, right? So that's what I'm going to write in the note, or the disjunction include the case both. So or included the case both, not just either or. It could be either or both. So because that include the both, we call this is the inclusive or. I mean, so we say the disjunction is the inclusive or. Clarify that, meaning including the case when both of them are included. If we don't want both, what we call it exclusive or, denote as XOR. So exclusive or denote by that XOR is the proposition that is true when exactly one of them is true and false otherwise. So true when exactly one is true and false otherwise. So let's say true, false, true, false, true, true, false, false. And it is true when only one of them true. Both of them are true here, so this will be false. And both of them false here, this is going to be false. And it's true when exactly one of them is true. Right, so that is exclusive or. Right. Next, we have conditional statements. Or should say, conditional proposition. Right. Conditional statement P implies Q. So there are a lot of ways to say that. We will on the next page for that. But it's denoted by an arrow. It say if P then Q, or use the right arrow to denote that. So it's conditional statement and denote as this. And we say if P then Q, or P implies Q. And it is false when P is true and Q is false. That is a little less obvious. And the first part, and the P, the one before the arrow, is the hypothesis or the antecedent or the premise. And Q, the second one, is the conclusion or the consequence. So there's a lot, but just keep in mind that it is false if the true implies false. Just go back to the disjunction and write this real quick. False or false is false. Everything else is true. Right. Now we construct a true table for the conditional statement. By the way, this is different way we can say it. If P then Q, Q follows from P, and then P implies Q. Those are the common way, but there's a lot of things we can say for the conditional statement. Right. This is what we call the true table, by the way. It has the true values or false for every different scenarios of each one of the proposition. So this includes every different scenarios. Right. Now, what did we say? It is only false if the true implies false. So this is false. And everywhere else true. Right? Now, just give you one example. So according to this, I might say like, if I am, say, Superman, then 1 plus 1 is equal to 5. It is true statement because that's one is false. After false, doesn't matter what it is, true or false, it's still true. So pay attention to this. Usually in the implication, if we start with false, doesn't matter what it start. What after that, it's always true. It is only false if we have a true implies false. So we say true implies false is the same thing as false. Make sure we use 3 bar. Go back and add a bar. Right. So true implies false is false. Now let's see. Can we use a calculator for that? I should not write it here. Okay, so of course I can show you, but a little bit about this. So we need a table, right? So we get a table, hit stat, hit the stat button, it says edit, hit enter. Right, so we have we enter the true false here and true false here. Again, 1 for true, 0 for false. 1 for true, 0 for false. Right. Now, on here we have to say it either the, let's work on all of the conjunction, disjunction, and then the implication in a bit. Right. The not is easy. Right. Now, this is the true table for the conjunction, right? So, be careful here. Go up, highlight the L3. It has to be highlight L3, and we say it's going to be this and this. So to get to L1, L2, you see that above the 1, 2, 3, there's a blue. If anything blue, hit that second button, second one for L1, and then we need N, right? Second, math, go to logic, N. So L1 and L2, and of course it's true when both of them are true and false otherwise. So that conjunction certainly works. Now if we want disjunction, we just need to change to OR. So if you want to clear the list, highlight the list, hit clear and enter. Never hit delete. If you want to delete the list, if you actually do that, it is a very bad thing, because that just delete that completely. And if it is the case, just have to delete everything after that and start anew. Second, this 3, this 4, wait, okay, this is next, and then calculator can handle 6 lists. Right, let's go back here. Alright, we have this one, this 2. Now we want to find the OR, or the disjunction. So second one, that list 1. Second math, we'll do logic. This time is OR. L2. Right, as you see, it is true everywhere else except false, false is false. For all false is false. Right? So yeah, calculator works. Alright, XOR, of course, second test, you certainly see the exclusive OR or the negation. So that's good. We can verify that easily. However, what we don't have is this. So what do we do if we want to construct a truth table for this? Well, if you want to do that in the calculator, go to the next section, section 1.3, we'll talk about that. But for now, just do this by hand. Alright, so next, we define the converse, contrapositive, inverse, equivalent statements. So the converse, here's the way we defined it. P implies Q is the conditional statement. The converse is Q and P, so pretty much we interchange P and Q. And then we have the inverse. Inverse is negation. Negation the hypothesis, negation the conclusion. So negation. Both statements. And then contrapositive. Contrapositive is going to be both. Interchange and then do negate both. Interchange and negate both of them. Right. When two compound propositions have the same true values, regardless of true or false, they said to be equivalent. Right. So I work on some example of those first. Right. For example, if the original statement is if you do it, then don't be afraid. Now we will construct the converse. Converse, we just interchange. Don't do anything else. So interchange, we said, if you don't be afraid. And then you do it. Right, so put interchange, don't do anything. So that is the converse. Next, the inverse. Inverse is where we negate both of them. If you, we have to turn this into negation. Do not do it. And then negation of this. Negation of this is when we take that negative of the don't out. So we say, if you do not do it, then be afraid. Of course, That is the negation of it. Now contrapositive. If you do it, don't be afraid, you have to interchange. I said, if you are afraid, so we bring that in front and negate that. Then bring this on the back and negate it. Then you don't do it. Right, so that's what we have. Right, I'll do the same thing for the next example. If it is a dog, then it's a mammal. So converse. Just interchange. If it is a mammal, then it is a dog. I just interchange. That gives us a converse. The inverse is where we negate both. If it is not a dog, then it is not a mammal. So we negate both of them. And contrapositive, we do both, negate and interchange. So this bring in front. If it is not a mammal, then it is not a dog. Right, so of course we just stick to definition, and that's what we have. Now just want to talk a little more of this. Based on this, if it is a dog and it is a mammal, we know it's true because a dog is a mammal, right? So it's true. The next one, if it is a mammal, then it is a dog. This is false because it could be a cat, a bear, or whatever it is. Inverse. If it's not a dog, then it's not a mammal. Well, that may be true, we've said, but in general, it's false. If it's not a dog, once again a cat, then it's not a mammal. That's false because the cat is still a mammal. So those are false. And if it is not a mammal, then it's not a dog. Now this is true. If it is not a mammal, so it could be like a crocodile, a fish, a turtle, a bird, something like that. Then it's not a dog because those are not a mammal and it cannot be a dog. Right. So as you see, the original statement is true in this case. The contrapositive is true in this case. So in general, original statement, original conditional statement, and the contrapositive, those two are equivalent. Just like the converse and the inverse, they are equivalent. That's what we write in the note on this page. Right. So we say conditional statement. The original one. Of course, all the converse, inverse, and the contrapositive themselves are conditional statement as well. But when we say conditional statement, here we refer to the original statement, which is equivalent to conditional statement is equivalent to contrapositive. And the converse is equivalent to inverse, because we will prove that in a bit. But that note I want to write here. Right, now if I live in Dallas, then I live in Texas. Actually, this is a very good example, but I didn't want to use that to verify whether it's true or false. I want to use this example to use true or false, and that will come up with this note. Because when I look it up, actually the city of Dallas, there are 9 other states that have the city of Dallas, so that it's not really unique here. So we cannot claim that there's only one Dallas in United States. But of course, conventional wisdom, when we talk about Dallas, we refer to the Dallas, Texas. Right. Now, of course, what we do here, of course, write the converse. The converse. I'm just going to flip here. I live in Texas. Then I live in Dallas. And then inverse is where we negate. If I do not live in Dallas, then I do not live in Texas. Of course, this could be the case. For example, if I live in Houston, then I still live in Texas, so that is false, right? So those two are said to be equivalent. If I live in Texas, then I live in Dallas. Again, I could live in other cities than Dallas, so those two are equivalent. And contrapositive. Contrapositive, we flipped and then negate. If I do not, I have to bring this in front. Live in Texas, then I do not live in Dallas. Right. So that is the conditional statement. Right. Yeah. Biconditional statement, we denote by the arrow going both ways. Is the proposition P if and only if Q. And the way we write that, we say P is necessary and sufficient, or if P then Q, and conversely, or P if and only if. So we denote if and only if by I and then FF. Right. And we say if and only if. Right. So true when they have the same true values. So this is why I said equivalent. So let's set a true table here. True, false, true, false, and then true, true, false, false. And the values, if they have the same thing, then it's true, otherwise false. Of course, we can just combine P implies Q and Q implies P both together, and that is what we have. Right. Next, precedence of logical operator. So we, like all the operation, we follow this negation first, conjunction, disjunction, and then the conditional or biconditional. Right. Now we go to this exercise. So construct the following table, the true values for all of this. Right. This will be fun. So let's start with this statement P. True, true, false, false, and Q. True, false, true, false. right? P implies Q. In the next section we will have a way to do that, but for now we just have to do this by hand. It said it is false. Focus on this case. When it's false, when true implies false. So this is where it's false. Everywhere else is true. Right, so that's the first one. Next, we have Q implies P. Now, the implications is important. The first one implied the second. We cannot interchange them. So this case we would say P, Q implies P. So we go from this column to that column. And when it said Q implies P, so we go Q first and then P. If it's true, implies false. Like that. This won't be false. Otherwise, it's going to be true. Right? True implies false. Remember, Q first and then P. So true implies false is false. Right, before we do the next two, we're just going to do the negation of P and the negation of Q. Negation of P, just turn everything true to false. Just say one thing, I didn't do it. So, false, true, and then not Q, false, true, right? Just turn the true to false and the false to true. Now we do is the not P and not Q. Not P, not Q, pretty much focus on this one. And this is false. When we have a true implies a false. Everything else is true. Now, the last one is not Q implies not P. So, meaning for this, from not Q implies not P. So the true not Q implies not P. So that is false. Everything else true. Now, when we look at this, what do we have here? So this is the conditional statement. Q implies P. So this is just interchange. So this is converse. And this is negation. So this is the inverse. And not Q and not P. This is contrapositive. And as you see, original statement and the contrapositive, they have the same true values. True or false are the same. So this and this are the same. If true are the same true false values, and the converse and the inverse have the same values. Right? So that's what we have on page 5. Right, and now we go to this example that have 3 proposition P, Q, and R. So we have one for each. Right? So P, Q, and then R. Right, now we just going to set on the one on the right, alternating true false. On the second one, alternating every true, false, true, false, and the one on the left, we alternate every 4, true, and then 4, false. With this, we cover every possible scenarios for all 3 of those. Right, next. So when we look at this, just like all the operation, we do see the negation. That's right, but we see the parentheses. So let's go with the parentheses. P or Q. Focus on P or Q. Q said it is false when both of them are false. So when we look for when both of them are false, false or false is false. Otherwise, at least one of them is true. So we're true. Right, that's first. Next, we have not or. So, not or. Yeah, I have to do the negation before the conditional statement. So this is all the operation. So not or. Just turn true to false and false into true. And finally, the last statement, P or Q, this one implies not or. Just going to use below for this one. So P or Q implies not or. So only need to focus on the last 2. This implies not or. Right. So remember, implication or the conditional is false when true implies false. Right? So this is false. That's good. That's good. Oh, it's false again. It's false again. And we don't have any of those scenarios. So this true. This will be true, and true. Right. If we use a calculator to verify this, we don't need to do the intermediate step. We just do the last one. Never mind. We cannot use a calculator because yet because we need the implication. Right. So like I said, the next section will say what is equivalent to the implication. Right. So with that, we finished the first section in discrete math. Thank you for watching and see you in another video of this series.